Is an explanation of the proof of the Pythagoras Theorem by Calcea Johnson and Nikira Jackson. What a fantastic piece of work this is. It's quite long, so I'm going to push on. We're going to take a standard triangle, ABC. C is the hypotenuse. We're going to show that c squared is equal to 2ab divided by sine alpha. Alpha's the angle up here. And then, well, that's the easy bit. Then we're going to show that a squared plus b squared is equal to 2ab sine 2 for sine 2 alpha, which obviously will show that a squared plus b squared equals c squared. The first bit is easy. The second bit is long and tricky, but there is a bit of fun at the end. The first bit we're going to use SOHCAHTOA, classic trig functions, and sine x, this being x, is opposite over hypotenuse. Opposite is this side here, the other end of the triangle. Hypotenuse is the long side. And we're also going to use the sine rule, which is my favourite trig relationship. It's brilliant for checking your answers to questions. And you look for Langles, which is a length-angle pair. And the length over the sine of the angle is the same for each of the angles. B over b equals c over sine c, etc., etc. Really useful. Anyway, let's push on. Here is the triangle that we're going to use. And the first thing we can say is if we're looking at the angle beta, this is the opposite. This is hypotenuse. And therefore, sine beta is the opposite over the hypotenuse is b over c. We'll use that later. Now, we're going to flip the triangle over to create two similar triangles. Here's the triangle we started with. Here is a mirror image. Same angles at the bottom, same angles at the top. And you can see that this collective angle is 2 alpha. And now we're going to use the sine rule. The angle here, 2 alpha, and the length this side is 2a. So 2a over sine 2 alpha is equal to length of c over sine beta. And it's c over sine beta. They're going the other way because it's an isosceles. So these are the two equations we've just seen, but we know that sine beta is b over c. So we can say that 2a over sine alpha equals c over b over c. I hate it when we get fractions on top of one another. So let's quickly multiply by c. Top and bottom of that side. So we get c squared on the top and just a b on the bottom. What do we do next? What do we do next? We multiply by b. 2ab divided by sine 2 alpha equals c squared. And if you remember, that's what we were trying to show. So we'll bear that in mind for later. These are the steps. C squared equals 2ab divided by sine alpha, and we've done that one. That was the easy one. Now things start getting a little bit more difficult. We're going to use this equation for the sum of an infinite series. X plus x squared plus x cubed, on and on and on, is equal to x over 1 minus x if x is less than 1. Because that's required, because these terms of x, powers of x, have to get smaller and smaller. Otherwise it doesn't sum. For example, if we're looking at a half here, x equals a half. Half square is a quarter, half cubed is an eighth, on and on and on and on and on, is equal to a half over 1 minus a half. Well, 1 minus a half is a half, so half over half is 1. Finally, half plus a quarter plus an eighth, on and on is equal to 1. This is the proof. I'm going to leave the proof though, we're not going to go through it, but if you want to stop the video and have a look at it later, by all means do so. But this is what we want. We're going to show this is going to prove that, what we need to prove. Right, here we are. I have extended this line down here, and I have introduced this line at an angle of alpha. Now we know that alpha plus beta equals 90 because the other angle in the triangle is a right angle, which obviously has 90 degrees. So alpha plus beta equals 90, and if this is alpha plus beta, then that is a right angle, which means that this whole thing is a right angle triangle. Now, We'll come back to that later. Let's fill in some other angles. This is beta. This is a right angle. This triangle is similar to this. Similar means the angles are the same, but the lengths don't have to be the same. And we can clearly see it's a different size. This angle, this triangle down here, is also similar. You see it's very similar to this triangle. That alpha is corresponding to that alpha, beta corresponds to that beta, because these are parallel. But it's smaller, but it's similar. This again is similar, and this again, well, that's another similar one. It just goes on and on and on. You can see they're getting smaller and smaller. We're going to call this length L1, this length L2, this length L3. There'll be a length L4, L5, L6. Then we're getting smaller and smaller. We'll have M1, M2, M3, ad infinitum. This is the series that we are going to add up using the formula that we were just looking at. Let's look at this triangle here. This triangle here is similar to this triangle. So we have a hypotenuse C, the short side A, and the long side B. Here we have the hypotenuse red C, short side red A, long side B. This side relates to this side, but it's been changed by what we call a scale factor. If we're going to find L1, we need to find the scale factor that maps this triangle, the original, onto this triangle. We know that B times the scale factor is equal to this B. But this B is equal to 2A. So let's forget about the B for a minute. B times the scale factor equals 2A. Divide by B, and we have that the scale factor equals 2A over B. Every side of this original triangle multiplied by 2A over B becomes the side length of this triangle. So this C is equal to C times 2A over B. Red C equals the original C times 2A over B. And so we found what L1 is. The first one of our lengths down this side. A. How long is this line here? Well, we're going to, just finding M2. This length here is X. And we know that that was the original A multiplied by this scale factor. So X is equal to A times 2A over B. It's also the B side of this triangle, because we're in here now. B here has been multiplied by a scale factor and become this length, this X. So B times the scale factor, this is a different scale factor which relates the triangle to this size, is equal to 2A squared over B. Again, we divide by B. So the scale factor is 2A squared over B squared. Every length in this triangle, every ABC, multiplied by 2A squared over B becomes this length here. So M1 clearly is C times 2A squared over B squared. Right, we'll remember that then. And now we'll look at Y, because this is the line between this triangle, which we're going to look at now, and the line and the values we know. This was A, but multiplied by the scale factor 2A squared B squared. So Y equals A times 2A squared over B squared, or equals 2A cubed over B squared. So let's find the value of L2 looking at this triangle. We know that the side B has become, because this is the long side, has become the length of Y. And we know that the length of Y is 2A cubed B squared. So B times the scale factor that relates these triangles to this triangle, and B times that scale factor gives you the length of Y, 2A cubed over B squared. So the scale factor, the new scale factor that maps this triangle, the original triangle, to this little one, is 2A cubed over B cubed. We've just divided by B cubed. So now L2 is going to be equal to C, the hypotenuse, the original hypotenuse, times this scale factor, 2a cubed over b cubed. So far so good. We'll introduce a new length here, which is z. We're doing exactly what we did for this one. Z was the original a multiplied by this scale factor. So z equals a times 2a cubed over b cubed equals 2a to the 4 over b cubed. That's z. And z, as you can see, was the original b multiplied by the scale factor that relates this triangle to this triangle. So to find m2, b times this new scale factor is equal to 2a to the 4 over b. And therefore we divide by b, so the scale factor that relates this triangle to this triangle is 2a4 over b4. And again, that means that m2 is c times 2a4 over b4. That's shrunk. And again, we'll remember that. So, where's this getting us? Well, let's have a look at this triangle again. This is a right angle triangle. We know that because alpha plus beta equals 90. This is 2 alpha. And we know that if that's the opposite, and that's hypotenuse, that sine 2 alpha is our opposite over hypotenuse. Classic. So the opposite is equal to L1 plus L2 plus L3 plus L4 plus L5 plus L6, which I haven't shown. And the hypotenuse is C plus M1 plus M2 plus M3 plus M4 plus whatever. Let's take a look at L1 plus L2 plus L3. We know that L1 is C times 2A over B. We know L2 equals C times 2A3 over A3 cubed over B cubed. If we did this again, we would find that L3 is C times 2A5 over B5, because each of these is being multiplied by A squared over B squared. That is what's happening each time we go down this triangle. So we are looking for an infinite series where x is less than 1 that we can sum. And here we can see that x is equal to a squared over b squared, because that's what you multiply each of these by. And we can produce this nasty little equation. Now, inside here is the infinite series, a squared over b squared, and then a squared over b squared squared, etc., etc., etc. And we can sum that, because we know that a is smaller than b, and therefore this is less than 1. But we need to get it right, because at the moment, this alone doesn't give us the lengths we know, L1. We need to fiddle it, in a sense. We need to bring this element in to make sure that this first multiplication gives us L1. L1 has a C, L1 has a 2, L1 only has a power of A, and we've got A squared, so we need a 1 over A, and it's only got a power of B underneath, a minus B if you like, and it's got a minus 2, it's B squared underneath, so we need to bring in a B. This will multiply to that times that will multiply to that, and so on and so on. But we can sum that because we know the formula for summing an infinite series where x is less than 1. And it's this. The opposite is 2bc over a, where times this little gem. This is where x is equal to a squared over b squared. A squared over b squared divided by 1 minus a squared over b squared. Again, I hate these. I hate having fractions on the bottom. So let's multiply by b squared. And we get this. The opposite is equal to 2bc over a squared, b squared minus a squared. You can see that this, when multiplied by b squared top and bottom, has the same value, but just gives us a squared on the top, and that b squared times the 1 gives us that, etc., etc. This is the easier side, but there's not much in it. Now we're going to have a look at the hypothesis. Hypotenuse. Right, the hypotenuse equals C plus M1 plus M2 plus blah, 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 just going ad infinitum. M1, as we know, is equal to C 2a squared over b squared. M2 is C 2a to the 4 over b to the 4. And I'm going to go out on a flyer. M3 is C, 2a to the 6, b to the 6. It's getting smaller and smaller. X squared, x plus x squared plus x cubed. In this case, x is equal again to a squared over b squared. But the good news is that it doesn't need to be fiddled quite so much, because we've got a squared over b squared here, and we've got 2c. So we have 2c, a squared over b squared, and then the next one is 2c. Oh, look at that, a squared over b squared squared. So we're off, and don't forget the c at the end. So this is the infinite series. A squared over b squared is less than 1 because a is smaller than b. So we can summarize this as 2c, a squared over b squared, 1 minus a squared over b squared plus c. Let's do what we did before, multiply by b squared to get b squared minus a squared on the bottom, a squared on the top, 2c there, 2c there. That is the hypotenuse. Now we come to the fun bit. Sine 2a equals opposite over hypotenuse, as we've decided. And the opposite is this, from the previous 2 slides ago. This, we've just worked out, the hypotenuse is 2c a squared, blah, 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 blah. Right. The good news is there's a c here, there's a c here, there's a c here. There's a c in everything. So we can remove that by dividing top and bottom by c. And so sine 2 alpha equals this. And I've tidied it up a little bit. What have I done? I've divided by a, so it's only 1a on the top. I've taken out the c, and there's the 2b. So 2ab on the top over b squared minus a squared. And on the bottom, I've taken out the c. I've put the 2 in with the a squared, and I've got c, 1 here because I've divided by c. Well, this is starting to look a bit tasty. Let's bring this 1 in here. And in order to do so, we put it over a numerator of b squared minus a squared. So the bottom becomes 2a squared, and then we add plus b squared minus a squared all over this b squared minus a squared, this common thing here. Right, well, we've got a numerator and a denominator, both of which are fractions, both of which have the same denominator. So we'll multiply top and bottom by b squared minus a squared. I told you this would be fun. Sine 2 alpha now equals 2ab. And on the denominator, we have 2a squared plus b squared minus a squared. Now we've got an a squared and we've got 2a squared. So let's subtract that. And now we've got 2ab equals a squared plus b squared. This is starting to look interesting. Let's multiply both sides by a squared plus b squared. A plus b squared plus b squared equals sine 2 alpha equals 2ab. And now I'm going to divide by sine 2 alpha. A squared plus b squared equals 2ab over sine 2 alpha, which looks familiar because that is what we were trying to prove, a squared plus b squared. And if c squared and a squared plus b squared both equal the same thing, then they both equal each other. And that is the proof. What a fantastic piece of work by 2 young girls. And where would you give it when you were doing this? Where would you say, enough, enough? You know, pressing on and on and on. This is the hardest page. These infinite series. Absolutely fantastic piece of work. And because I can't edit and can't operate the machinery, I'm going to leave this for a few seconds before I disgracefully bow out.